Welcome you all to today's session on characteristics of thyristor. We will see what is VI characteristics of a thyristor. We will look into the turn on as well as the turn off characteristics of thyristor in this session. So first, coming to the VI characteristics of thyristors. So to explain this VI characteristics of thyristor, I need the structure of the thyristor. So I will draw the structure. That is, we have already seen in our previous videos, where the thyristor is a 4-layer device, which is PN. This is the gate terminal. We have the cathode terminal. We have the anode terminal. Always remember, we apply anode voltage with respect to the cathode as well as gate supply with respect to the cathode terminal. So we have already seen how this thyristor operates as a latching device. So we will write the 3 junctions, namely J1, J2 and J3. So this junction is J1, the second junction is J2 and this junction is J3. Okay. So first, this thyristor, it always operates from the non-conducting state to the conducting state. Okay, mainly your thyristor has 3 modes of operation or 3 regions of operation. First region is forward blocking state, and the second one is forward conduction state, and third one is reverse blocking state. So forward blocking state, forward conduction state, and third one is the reverse blocking state. So let us see where are these 3 states and how the thyristor is going to operate. So if you observe here, the x-axis is the anode to cathode voltage and the y-axis is the anode to cathode current or IT. So instead of writing it as IT, that is thyristor current, even you can write it as IAK. It is fine. Anode to cathode current and x-axis is anode to cathode voltage. This third quadrant is the negative side. Okay. And now coming to how it is going to work. So you can observe here you have 3 junctions, J1, J2 and J3. So initially, if we make anode voltage positive with respect to cathode, so first condition we will take VAK positive, that means anode voltage is positive with respect to the cathode, then the junctions J1 and J3 will be forward biased. So if VAK is positive, our junctions J1 and J3 will be forward biased, whereas the junction J2 will be reverse biased. So J1 and J3 forward biased, whereas J1 and J3 is forward biased, whereas J2 is reverse biased. So in such a case, very small leakage current will flow from anode to cathode. In that condition, we say that our SCR or the thyristor is operating in the forward blocking or off state condition. So that is this region, okay, this region, forward blocking region, wherein only a leakage current flows in the forward direction. So this is your forward blocking state. Forward blocking state. The leakage current which flows is the forward leakage current, which is very, very small. Next, if we increase the anode to cathode voltage to a sufficiently large value, that means if you keep on increasing this VAK in the positive direction itself, then what will happen is the reversed biased junction J2, it will break. That is called as avalanche breakdown, and the corresponding voltage you call it as a forward breakover voltage. Forward breakover voltage is nothing but you keep on increasing the anode to cathode voltage until the junction J2 is reverse biased. So how are you going to identify it? During that time the forward voltage drop will be less and your device will start to conduct. So actually this is one of the method of turning on the SCR. You keep on increasing the anode voltage without applying the gate signal, it will conduct, but it will cause a damage to the device. That's why we don't go for it. Okay. So forward breakover voltage is the anode to cathode voltage which will make your device to conduct without applying your gate signal. So now what is the conduction state? So conduction state is you can apply a gate signal. Okay, the junction J2 will be forward biased. So J2 can be made forward biased in two ways. J2 can be made forward biased in two ways. One is by applying the anode to cathode voltage, or the other one is by applying the gate current. Okay, anything is okay, but we go for this second method, that is the gate current method we go. So this junction J2 is made forward biased and your device will conduct. So this region is nothing but the forward conduction state. Forward conduction state. So once the device starts conducting, you can observe the drop, the forward voltage drop is very less. This is somewhere here. Say we can say around 0.5 to 1. So once you always remember that once the thyristor starts to conduct, the forward voltage drop across the thyristor will be in the region 0.5 to 1. So usually 0.7 to 1 volt you will have, and you can see the current being very high. The current is very high. So I'll repeat this. So if you apply anode to cathode voltage which is positive, junctions J1 and J3 will be forward biased, J2 will be reverse biased, and a small leakage current will flow. So this particular region is your forward blocking region. Forward blocking region. Once you make junction J2 forward biased, either by keep on increasing VAK or by applying gate signal, the device will conduct. So it enters the forward conduction state. Forward conduction state, forward blocking state to forward conduction state. So that is the transition which you can observe here. See, forward blocking state to forward conduction state. Once it is in the forward conduction state, the voltage drop across the SCR is very less, in the range 0.5 to 1, usually 0.7 to 0.9 volts it will be there, and you can see that the anode current is very large. Okay. And you see here there are two currents mentioned. One is holding current and the other one is the latching current. So these two are very important terms, latching current and holding current. So what is meant by this latching current? Latching current means the anode current should be sufficiently high so that even if you remove the gate signal, the device has to conduct. That means to say at this point, that is the latching current should be the one wherein the anode current should be high enough and you have to remove the gate signal, then also the device has to conduct. So at the latching current your gate signal should be 0, that means the gate current should be 0. So even if once the device has started to conduct, the anode current is sufficiently high, you have to remove the gate signal, then the device will conduct on its own. That minimum current which is required for the SCR to conduct, even if you don't have the gate signal, you call it as latching current. Then what is the holding current? Holding current is the one below which the device is going to turn off. Okay. So holding current is nothing but the minimum anode current required to maintain the thyristor in the on state. Always the holding current, always your holding current is less than the latching current. The holding current is less than the latching current. This is very, very important. So, holding current is the minimum current required to maintain the thyristor in the on state, whereas latching current is the current which is required to make the thyristor conduct even if you don't have a gate signal. So, these two terms are very, very important. So, now what will happen if we apply different values of gate current? So, if you apply different values of gate current, obviously the forward blocking voltage or the forward break over voltage, no, it is going to reduce. So, see here, say Ig3 is greater than Ig2, which is greater than Ig1. So, if Ig3 is large, what is V3? V3 is less. So, as it is. So, if Ig3 is very high compared to Ig1, then V3 is very less compared to V1. So, this is nothing but for different values of gate current, how your forward voltage, the break over voltage or the forward blocking voltage is going to decrease. Next, we will see the turn on and turn off characteristics of S. So, coming to the turn on characteristics, you can observe here we have gate current versus time, the anode current or the thyristor current versus time. If you observe here, once the gate signal is applied, simultaneously your anode current is not going to increase. It has a delay. Okay, there is always a delay for the thyristor to conduct when you apply the gate signal. So, this you can observe here T on, which is nothing but the turn on time, is the sum of delay time and rise time. So, TD is the delay time and TR is the rise time of the thyristor. Okay, delay time and the rise time of the thyristor. So, this collectively is your on time of the thyristor, TD plus TR. So, what is on time T on? This on time T on is nothing but the time interval between the 10% of the steady state gate current and 90% of the anode current or the nothing but the thyristor on state current. So, when your gate current is 10% of the maximum value and when your thyristor current has become 90% of the maximum value, that means the thyristor has started to conduct, that total duration you call it as turn on time. Then what is meant by delay time? Delay time is the time interval between 10% of the gate current to 10% of the thyristor current. So, you can observe 10% of the gate current to 10% of the thyristor current, whatever increase that duration is there, that is delay time. Whereas rise time is the time interval between 10% of the thyristor current to 90% of the thyristor current. So, always when we are designing a gate control circuit for the thyristor, we should remember the 3 points. So, the first point is once the thyristor is turned on completely, we have to remove the gate signal. So, gate signal usually it is in the form of a pulse. So, why we have to remove gate signal? So, if you keep on continuously applying the gating signal, there will be a huge power loss in the gate junction. Okay, and always remember we should never operate the thyristor in the third quadrant. So, the reverse blocking state. Reverse blocking state is when the anode to cathode voltage is negative, the thyristor is reverse biased. During that time we shouldn't apply any gate signal. Okay, that is our third quadrant region is nothing but our reverse blocking state. I forgot to tell you. Next, the second point is when the thyristor is reverse biased, we should not apply any gate signal. Else what will happen? The thyristor will get damaged due to the reverse leakage current. Next, the third point which is very, very important is the width of the gate pulse. Width of the gate pulse is nothing but the duration of the gate pulse. It should be always longer than the time required for the anode current to increase to the latching current value. So that is nothing but, in simple words, the duration of the gate current or the time interval of the gate current should be more than the turn on time of the thyristor, else it will not latch. That is why it is required. This is regarding the turn on characteristics of the thyristor. Next, coming to the turn off characteristics. So when the thyristor is to be turned off, the first thing what we have to do is we have to make the forward current to fall below the holding current. So we have seen what is holding current, right? So we have to make the thyristor turn off, we have to reduce our anode current to fall below the holding current. So if you have various techniques to make anode current fall below the holding current. Okay, if we are operating the thyristor with an AC supply, no problem. At every current zero crossing, we have a reverse voltage which applies across the thyristor and it gets turned off automatically. But if we are using a DC supply, we know that our supply is constant. You don't have a reverse voltage which gets applied across the thyristor. So what we have to make is we have to forcefully reduce the anode current to 0. Okay, so we have to have an extra components. So that extra circuit, you call it as commutation circuit. Commutation is nothing but turn off process of thyristors. So we should have a commutation circuit for an SCR if we are using a DC supply. So if we are using a DC supply, we need to have a commutation circuit. If we have a DC supply, to get a negative voltage across the anode and cathode, we need to have a commutation circuit. So commutation circuit is nothing but a circuit to turn off the SCR. So here once we make a reverse voltage appear across anode to cathode, is similar to a diode which is reverse biased. So a diode, when it is reverse biased, you know that it has a reverse recovery characteristics. So the outer two junctions, that is J1 and J3, it will exhibit the reverse recovery time which is TRR. Okay, this one, reverse recovery time which is TRR, and you can observe the recovery current is at its negative peak and slowly the current reduces to 0. So you can see a recombination time which is written as TGR. So that TGR is nothing but we have a inner PN junction which is J2, right? It requires time to recombine the excess carriers. So that time we call it as recombination time. So the reverse recovery time and the recombination time collectively is TQ, which is the turn off time. Okay, it is the turn off time TQ. It is defined as the minimum value of the interval between the instant when the on-state current is reduced to 0. See here, the on-state current is reducing to 0, and the instant when the thyristor is capable of withstanding the high forward voltage. So that is this duration. So after this, what will happen? The current is going to increase slowly. That depends on our supply. So we have to make the thyristor turn off, means we have to make anode current 0. So to make anode current 0, we have several methods. So the first thing is we have to reduce our anode to cathode current below the holding current. So to make our anode current fall below the holding current, just reverse the polarity of anode and cathode. That means we make anode and cathode negative. So if we make negative, reverse voltage appears across anode and cathode. J1 and J3 becomes reverse biased. J2 should also be reverse biased. So it takes some time, that is called as recombination time. And you can see TC. TC is nothing but the circuit turn off time. So always our circuit turn off time should be greater compared to your gate turn off. Okay, your anode turn off time. So your entire circuit should turn off last. not first. So that you have to keep in mind. This is all about the turn off characteristics of thyristors. So we have seen the Vi characteristics of thyristor, what will happen to the Vi characteristics if we vary the gate current. We have seen the turn on characteristics and the turn off characteristics of thyristors. So we can make our thyristor to conduct without the gate current provided our anode current is very large, okay, and it has started to conduct on its own, nothing but it has latched. And we can turn off a thyristor by making the current reduce below the holding current. If to reduce the current below holding current, just reverse the polarity of anode and cathode. That means Vak we have to make negative. So to make Vak negative, if AC is applied, then it is very easy. During negative half cycle, Vak will be negative. But if we use DC, we have to go for an external circuit. That external circuit is called as the commutation circuit. Okay, that's all for today. So the next session we will see the different types of thyristors. Thank you.